For question 13, we have a bridge rectifier. So for this bridge rectifier, we know that the voltage at the secondary is 12 sine omega t, right? That's the 12 volts is the peak of Vs. We need to draw the input and output waveforms on the same graph, assuming all diodes are ideal. And also what would be the DC content, or like the average voltage, and what would be the peak inverse voltage rating for the diode work properly as in this full wave rectifying circuit. So for this particular problem, we know that, well, let me draw the circuit. So we have Vs here, right? Then we have a diode here, another one here. Then we have the load here, another diode here. This goes back here, and this is just the ground. Okay, so we have Vs, right? Sorry, we have Vs here. Now, during the positive cycle, when we have Vs greater than 0, this potential here is greater. Suppose we have 12 volts here, right? So the current would flow in this direction. So it would flow right in this direction here, right? But it would be blocked in this direction here. Okay, so if you just want to ignore this ground here, it would flow like this way here. Okay, so that's the direction of the current. Now if we are on the second half cycle, this would be minus 12 volts. Like I'm just considering like the peak value of the voltage. Okay, so in this case, this potential minus 12, it's greater than the potential that we have here at this node, and then the current would flow in this direction here. So current will be blocked in this direction here. Okay, so let me put blocked. Okay. Now if you look at the direction of the currents through the load, it's going this direction. In here it's going this direction. So in both half cycles, the current is actually flowing the same direction through the load. So the bridge rectifier, it has the same graph as the full wave rectifier that we just plot on the previous exercise 12. So here's just 12, here is minus 12, we have again 1 over 60, 1 over 120, right? So we have the input here, and then the output would be the same here and here. Okay, so this is the plot for V out, VI, V out. Now for the peak inverse voltage, okay, so if you look at the circuit, it basically means that the voltage that a single diode has to hold, because we have the ground there, is just the voltage here. So suppose we have one diode here conducting, right? Then we have the load, we have another diode conducting here, and that goes back to the source. But this one here, it's an open circuit, right? So we have the ground here. So if this one here, suppose we are in the positive half cycle, this would be 12 volts, or just in a general form Vs, right? So the voltage that it needs to hold, like the inverse, right, voltage that it needs to hold, is just the same value as the source voltage. So in this particular case, P inverse voltage is just equals to Vs. And that's because it's an ideal diode. Remember that for a non-ideal case, we would have like some voltage, some voltage for like the battery model. Suppose we're using just the battery model, so we would have like still this to consider in the peak inverse voltage. So that would be the case for the potential that it needs to hold. Okay, but in this particular case, it's just the peak voltage of the voltage source, so it's 12. Now for the average voltage, it's just the same way as we calculated on question 12, right? So we have V average, and because the output it has the same shape on both half cycles, we can like just multiply by 2. So the entire period is 1 over 160, so it's times 60 times 12 integral from 0 up 1 to 120 of sine of 2 pi 60 t dt, and that gives us an average voltage that it's 2 times 60 times 12 minus, right, because the integral of sine is cosine of 2 pi 60 t from 0 to 120, and the average voltage is just 7.64 volts in this case, the average. Okay, that's it for this problem.